join me as we explore the universe as part of the Great Minds series. Astronomy is as old as humanity itself. When I moved to Australia, here to the lands of the Ngunnawal Ngambri people, people who have inhabited the lands of Australia for more than 60,000 years, I learned of a story of seven sisters based on the asterism in the sky known as the Seven Sisters or the Pleiades. And this Aboriginal story was used to allow people to navigate around the countryside and was sung as a song. The story where one of the sisters went out and fell in love and left the other six in a not a very nice way is exactly the same story that I was taught as a child when I grew up in the United States, based on the Greek mythology, the Pleiades. Now, this story connects our humanity back to time immemorial, back to when we were one people with the same culture and history. Astronomy has been used by all people, and the Pleiades, because it's at the celestial equator, has been seen by every human ever born, because they go back, those stars, 80 million years, well before humans' ability, humans' species. So astronomy goes back to the foundations of humanity and has been used to chart the seasons. But it's also been integral to the development of science itself and humanity's ability to go through and progress. If you ever have a chance to look up at the Pleiades, it's one of my favorite things to look at in the sky. 6 stars there for 80 million years. There's many, many hundreds of stars if you have a telescope. If you go through and look in a cave in the south of France, Lascaux, in that cave, there is a very famous picture many will have seen of a bull. And on the shoulder of that bull is the Pleiades, the 6 stars. And the reason that bull is there with the Pleiades there is because that turns out to be the constellation Taurus, the same one we know today. And so once again, we see those stars and the stories dating to prehistory. Science sort of began, I think, in astronomy with Ptolemy. Ptolemy developed a very elaborate system to predict the motion of the planets in the sky. As a Greek, he stuck with the idea of axioms. And to the Greeks, there was a few axioms. The Earth is at the center of the universe, and things, all celestial bodies, travel on circles. They didn't really ask questions around those ideas. They were taken as given. And within that framework, Ptolemy was able to create an elaborate system of epicycles, of circles within circles within circles, that was very accurate in its ability to trace out the planets as they traversed the night sky. And that served as the best way of charting the planets through time, right through the Western Middle Ages and Dark Ages, we call them. And it really wasn't until we had Copernicus come along. Copernicus challenged one of those axioms, which is that the Earth is the center. He said, I think I can make this all much simpler if I put the sun at the center. And thereby came a great achievement for humanity, where we were able to give up an idea held for literally thousands of years, that the Earth must be the center. And this Copernican ideal allowed us to essentially rethink the cosmos and our place in it. Now, it turned out that Copernicus' system, aesthetically pleasing because it was simpler than Ptolemy's, actually didn't do a better job at predicting the paths of planets in the night sky. We went through and started with Tycho Brahe, a Swede who later moved down into Czechoslovakia, who started measuring very accurately the positions of the planets. And you could see that both Copernicus's and Ptolemy's way of doing it was not entirely accurate. And he worked with a person named Johannes Kepler. And Kepler started adding mathematics of new forms to Copernicus's ideas. And he was able to triangulate especially the planet Mars. And he saw that Mars was moving not as a circle, but as an ellipse. First step of science where you actually use measurement to challenge ideas and you start to reform the ideas. So Kepler came up with 3 laws, one of which is that planets travel on ellipses, and he was able to create a mathematics that we still use today when we teach astronomy. But it was Galileo who really advanced things to the next level. Galileo developed the telescope. He didn't really invent it, but he used it for the first time to start exploring the cosmos. And he was able to thereby test Copernicus's idea by looking at, for example, Jupiter. Jupiter had 4 moons, and he could see that the moons were definitely going around Jupiter and not the Earth. Clearly, the Earth was not the center of everything. But he was also able to look at, for example, the planet Venus. Venus showed phases like the moon, and when Venus was small, it was full because it was behind the sun, fully illuminated. When Venus got very big, it had the shape of a crescent moon because it was only partially illuminated, and this is exactly what Copernicus's theory predicted. He could go through and demonstrate for the first time Copernicus was right and Ptolemy was wrong. This was the beginning of the scientific revolution, steeped in astronomy. Isaac Newton, of course, took it to the next level. He was able to go through and break things down into the nature of Newton's laws, and going through and thinking of forces and how gravity works as a force. And from first principles, was able to go through and say, if I think gravity works, that the force depends on the square of the distance and the mass of the object, he could actually derive, using calculus, which he also helped invent, that planets must travel on ellipses. And thereby we connected ideas, mathematics, prediction, and theory, the basis of science today. And so Newton allowed us, for example, when Halley's Comet came in, to predict its orbit. And indeed, Newton's laws got the answers exactly right. A challenge to Newton came about as our observations got better. Telescopes were used in 1781 by Herschel to discover a new planet Uranus. Uranus slowly traversed around the sun, never discovered before because it was too faint. You need to have this new technology to see it. But when we plotted Uranus's motions, they weren't quite right. Newton's laws did not quite predict the motion across the sky perfectly. Was Newton wrong? Well, someone had an idea. Verret, a French astronomer, realized that you could understand Uranus's orbit if there was just another planet, the planet Neptune, which he predicted the position, and very soon after, Neptune was actually discovered by Verret's prediction. And so Newton vindicated. The theory was not wrong, rather the theory was right and was unable to predict the existence of another planet. Here we see the progression of science being falsifiable, but also predictive. As long as science continues to predict what we see, we treat it as true, a true theory. Now, we suspect most theories that we have in science are not exactly correct. We're continually looking for how to improve them through seeing if their predictions are right. Now, one prediction of Newton was not right, which was the orbit of Mercury. Mercury's orbit almost exactly went as Newton described, but there was one thing wrong. The orbit precessed, that means the ellipse, turned a little bit in space over time faster than what Newton's theories predicted. We went out and we looked for a planet that might cause this, the planet Vulcan. It would have to be very close to the sun, very hard to find. But that planet Vulcan was never discovered. Still to this day, and we're pretty sure there now, it's not there. Einstein, though, came along in 1905 and had an idea. A very simple idea, which is that he saw someone fall off a roof. And as the person fell, he thought, not that I should call an ambulance, but rather, I think that person doesn't feel gravity. And I think that his acceleration exactly counterbalances gravity. And I think that must always be true in this universe. So from that thought, he mathematically figured out the implications. It took him 8 years. And he had to learn tensor calculus, which was just being developed at the time. And in the end, the only way he could reconcile that thought with reality is that space must be curved and the laws of gravity must be a little different than Newton's laws. The first thing he could predict, it turns out, was that Mercury's orbit wouldn't be quite as Newton predicted, but rather as observed. But he also predicted that we should go out and we should see light bent, for example, of stars behind the sun during an eclipse. And so that test of general relativity was made in an eclipse in 1919 by Eddington, a great English astronomer. And in 1920, Eddington announced to the world that indeed Newton's laws were not correct. Einstein had thought, from thought alone, how to change those ideas and has predicted the universe and gravity as we now know it. That thought is a very rare thing that happens in science indeed. Normally, science evolves by fixing problems. Einstein's advance was done, like Copernicus, by aesthetics alone. These are almost two unique cases of that happening in science, but two very powerful advances that set the stage to modern science as we know it today. So telescopes, of course, ended up vindicating Einstein's theory of general relativity because we could go out and measure things and see if they are true. To this day, we have never found a way that Einstein's theory of general relativity has been wrong. But we keep looking, and indeed that has been a quest of my entire life is to go out and to test through the stars to see if Einstein's theory of general relativity explains nature as we see it. So you can see that astronomy goes back to the foundations of humanity and has taken us to this day, into the 2020s, and it has served as the catalyst for the development of science and the development of humanity. A very powerful tool that continues to be the frontier of human knowledge and the frontier of human discovery.